Hello, and welcome to this virtual lecture course on electromagnetism. I'm Dr. Andrew Mitchell, and in this lecture I want to talk about electromagnetic potentials. In the first part of this course, we considered the static limit of electrostatics on the one hand and magnetostatics on the other, and we saw that we could describe the electric and magnetic fields in the static limit in terms of potentials. We can derive the electric field in terms of a scalar electric potential and the magnetic field in terms of the magnetic vector potential. However, in a dynamical system where the electric fields and magnetic fields are changing in time, and the charge distributions and current distributions are changing in time, this all gets mixed up. So what are the implications for the potentials? In this lecture, we'll derive the electrodynamical potentials, and we'll see that this actually reveals a more deep and profound way of looking at the theory of electromagnetism. We'll also see how the potentials have a hidden local symmetry. These are so-called gauge symmetries. These symmetries are not just like global symmetries corresponding to a rotation of our coordinate system, but a local symmetry that can be applied point to point in space and also changing in time. We can exploit these gauge transformations to simplify some of our equations. And in fact, one particular gauge, the so-called Lorentz gauge, can be used to cast the potentials in the form of an inhomogeneous wave equation. This simplifies massively some of the calculations, and we'll see some explicit examples of that. There's an alternative way of looking at the potentials, so-called retarded potentials. And this embodies the fact that if I want to know the electric and magnetic fields here at a particular point in space at a particular time, then what I need to know is not just the charge distribution and current distribution in the rest of the space surrounding the observer, but also the history of those fields. And that's because information about the charge distribution and current distribution at distant points from the observer takes a certain amount of time to come in. The maximum speed that the information can travel is, of course, the speed of light. So these retarded potentials contain not only the information about these current distributions and charge distributions, but the history of those fields. Furthermore, we can use this concept of the retarded potentials to finally understand the electric fields and magnetic fields that result from a moving point charge, moving at some particular velocity and maybe a certain acceleration, and we'll see how the electric and magnetic fields become quite distorted relative to the static limit. Finally, we will revisit the idea of the quasi-static approximation, and we'll generally explore the consequences of the potentials and gauge transformations in the theory of electrodynamics. This will also set the scene for our future lectures, which will be on the relativistic formulation of electrodynamics, which will utilize this potential formulation. So let's get down to work.
In this lecture, we'll be discussing electrodynamic potentials. The most basic question in all of electromagnetism is, given a charge and current distribution ρ of r and t and j of r and t, what are the electric and magnetic fields, the E's and the B's? Once we know the electric and magnetic fields, we can use the Lorentz force law to see what the effect is on charged particles or currents. Of course, we know the answer to this. The answer is through Maxwell's equations. Maxwell's equations tell us how the source fields ρ and j are related to the electric and magnetic fields E and B. However, as we'll see in this lecture, there's a much more powerful formulation involving potentials. We already saw on the static side of the theory, when the charge and current distributions do not depend on time, so that the electric and magnetic fields are time independent as well, we saw that we could introduce an electric potential, which is a scalar potential, and we also saw that in magnetostatics we could introduce a vector potential, which is a magnetic vector potential. But when we consider a dynamical system with time dependence to all of the fields, time dependence to the charge distribution, meaning charges moving around, and time dependence to the currents, meaning changing currents, then the electric and magnetic fields are also time dependent. And from Maxwell's equations, of course, we know that the electric and magnetic sides of the theory then do not decouple and everything gets mixed up together. So what is the implication for the potentials? Can we still come up with a formulation of Maxwell's equations in terms of potentials? And the answer is, of course, yes. We'll see that that's a very rich and powerful theory, and that's what I want to talk about in this lecture. First of all, let's remind ourselves of the situation in the static limit to motivate this. Let me just very, very quickly summarize the situation in the static limit. Let's look, first of all, at the electrostatic case. In electrostatics, we know that the curl of the electric field is equal to 0, and this motivated the introduction of a scalar electric potential defined as being through this equation. So we imagine that we take a electrostatic scalar potential V, we take minus the gradient of that, and that gives us the electric field. And we can write that because we know that the curl of the gradient of some scalar field F is equal to 0 automatically by the power of vector calculus. So by defining the electric field as the gradient of a potential, we automatically fulfill one of Maxwell's equations, which is this constraint equation that the curl of the electric field is equal to 0. Likewise, on the magnetic side, we know that the divergence of the magnetic field is equal to 0. This is a weaker constraint because this is a single scalar equation, whereas the curl of the electric field equals 0 is actually 3 scalar equations. But notwithstanding that, we can still utilize the power of vector calculus to incorporate this constraint equation into the definition of the magnetic field through the potential, and we say that the magnetic field is the curl of a vector potential B. And again, the reason for that is simply that if I take the divergence of the curl of some vector field lambda, this is equal to 0 automatically, again, by the power of vector calculus. You can really just work this out from scratch yourself for arbitrary fields f and lambda, and you'll see that this always holds. And so the philosophy here is that we define the electric and magnetic fields in terms of potentials to automatically fulfill these constraint equations. Things are a little bit more complicated, however, in the dynamic case. Whilst we still have that the divergence of the magnetic field is equal to 0, this is basically saying that there are no magnetic monopoles. At the time of writing, this is what we believe. We still have no counter-evidence that there would be any such thing as a magnetic monopole, so we believe that the divergence of the magnetic field is equal to 0. Again, this does still imply the existence of a vector potential A defined through with the magnetic field defined through the curl of A. However, things are not quite so simple on the electric side of the theory because, of course, we have Faraday's law. The curl of the electric field is no longer just equal to 0, but minus dB by dt. And in the dynamic case, this is not just equal to 0. So we cannot just invent a scalar potential whose gradient is equal to the electric field. But we can use the definition of the magnetic field in terms of the vector potential in this equation. We can write this instead as minus d by dt of the curl of A. I simply used in here this expression. And because we have different partial derivatives in there, one with respect to time and one with respect to space through this nabla derivative, I can easily just swap the order of those things and write this as minus the curl of dA by dt. And this is interesting because now, on both sides of the equation, we have the curl of something. So here we still have the curl of the electric field, and now that's equal to minus the curl of the time derivative of the vector potential. And so we can just rearrange this equation a bit to write the curl of the electric field plus dA by dt is equal to 0. So on the static side of the theory, we saw that the curl of the electric field was equal to 0. In dynamics, we still have the curl of something is equal to 0, but it's not just the electric field, it's the electric field plus the time derivative of the vector potential. And so what this means is that we can introduce a scalar potential, which in dynamics is not called V, but called phi, such that if we take minus the gradient of phi, we would get E plus dA by dt. And again, this follows from exactly the same logic, because if I take the curl of the gradient of phi, that is automatically equal to 0. So what this means, finally, is that I can write down an equation for the electric field in terms of potentials, just as we wrote down an equation for the magnetic field in terms of the potentials. The electric field is defined as being the gradient of the scalar potential, just like in the static case, plus this extra piece, or actually it's minus dA by dt. So these are the fundamental equations that we need in this lecture. Very quickly, we've derived that the magnetic and electric fields are related to the vector and scalar potentials. So here is a summary of those two important equations. Again, we can write the magnetic field as the curl of the vector potential, and the electric field as minus the gradient of the scalar potential, minus the time derivative of the vector potential. So you can see that in the dynamical world, we need to know both the scalar potential and the vector potential in order to work out the fields. And so expressing the electric and magnetic fields in this way through the potentials automatically fulfill 2 of the 4 of Maxwell's equations. But what about the other 2 of Maxwell's equations? Well, of course, we have Gauss's law that the divergence of the electric field is equal to the charge density divided by epsilon naught. So let's just substitute in our expression for the electric field in terms of the potentials into this equation. Then we get that the divergence of minus the gradient of the scalar potential minus the time derivative of the vector potential is equal to the charge density divided by epsilon naught. And rewriting this a little bit, we can now express it in the form of a modified Poisson equation, where we have the Laplacian of the scalar potential here, plus the time derivative of the divergence of the vector potential is equal to minus rho upon epsilon naught, the charge density divided by epsilon naught. So this is like the Poisson equation, except that we have this additional term here. And this replaces the conventional Poisson equation in electrostatics that we studied in previous lectures. In this case, we have this additional time-dependent term here. In the static limits, this term would disappear, and we'd get the usual Poisson equation that we studied already in electrostatics. And it is this term, of course, that accounts for the time dependence. So this is one of the new equations that we get in the dynamical world when we cast everything in terms of our newly found dynamical potentials. This is replacing the Poisson equation. What about the fourth of Maxwell's equations, the Maxwell-Ampere law? Remember that the curl of the magnetic field was equal to mu naught times the current density according to Ampere, but in the dynamical world we have to include the Maxwell correction, which involves the time dependence of the electric field. So here is the Maxwell-Ampere law. What can we do with this? Well, let's apply the same strategy. Let's replace in this equation the magnetic field B by the curl of A, and let's replace the time derivative of E with the expression for the electric field in terms of the potentials, namely minus the gradient of the scalar potential minus the time derivative of the vector potential. So what do we get when we substitute those expressions in? Well, we get this expression, which looks a little bit messy. On the left-hand side, we have the curl of the vector potential. And then on the right-hand side, we have a term involving the gradient of the time derivative of the scalar potential. Again, I swapped the order of the derivatives here, which I'm allowed to do because they're smooth differentiable functions, and these partial derivatives are with respect to different variables. And then the final term involves the second time derivative of the vector potential. In magnetostatics, we saw that we were able to cast the Ampere law when writing it in terms of the vector potential, in terms of something that looked like the Poisson equation, yet again. However, that's not possible in the dynamic case, and in fact we get a zoo of terms when we expand out this curl of the curl here on the left-hand side. And the best we can do is write it in this form. Okay, so this is the final result, and we see that it's rather complicated. There's not really much more simplification that we can do. So what we've achieved here is to write Maxwell's equations in terms of the potentials, and we just have these two equations now. So Maxwell's equations are of course 4 equations, and we've reduced it down to these 2 equations. We started with 6 components for the fields, 3 components of the electric field and 3 components for the magnetic field, and these have now been encoded in 4 components of the potentials, 1 for the scalar potential and 1 for the vector potential. So clearly we've achieved some kind of simplification, but these equations are still in this form rather hard to solve. However, as we'll see, there are certain properties of these potentials that allow us to reformulate the problem in a more powerful way. So the idea of a gauge transformation of the electromagnetic potentials is that there is a hidden or internal symmetry in these potentials, and that means that we can make transformations of those potentials without changing physical observables, such as the electric fields and magnetic fields, the forces, the energies. So basically anything actually physically observable will be blind to these transformations of the potentials. And we already saw a couple of examples of this in the study of electrostatics and magnetostatics. For electrostatics, if we have an electrostatic potential, we know that that is defined arbitrarily up to some reference point. We can add a constant to our potential, and that doesn't change any physical property. For example, the potential difference, which is related to the energy, of course the constant cancels out. Or we could take the gradient of the potential to find the electric field, which is then in turn related to the forces on charged particles and so on. The forces and the electric fields are observable quantities, but adding this constant to the potential is not observable, because when we take the derivative, again, this just drops out. So that was one very simple example of a gauge transformation that we saw in the theory of electrostatics. We can simply add on a constant to our scalar potential, and it doesn't change the physical observables. Likewise, in magnetostatics, we saw that we could add on a constant to our vector potential. This time, the constant is itself a vector, but we saw, again, because we're taking derivatives, when we find the magnetic field, this constant drops out. In the dynamical theory, where we have these more general potentials, we'll see that actually there is a wider class of things that we can do to our potentials, whilst still leaving the physical observables unchanged. And this is called a gauge freedom, and to go from one gauge choice to another gauge choice is called a gauge transformation. So the key point is that these electromagnetic potentials have within them a gauge freedom. What this means is that we can freely choose any gauge that we want. Physical observables, on the other hand, are gauge invariant. They do not depend on our choice of gauge. A corollary of this, of course, is that if something is gauge invariant, then it is observable. Anything that depends on the gauge choice cannot be observable, so the potentials themselves are not observable. Choosing a particular gauge is called gauge fixing, so we actually have to do this to perform any actual calculation, but of course the results of the calculation will not depend on our gauge choice. And transforming from one gauge to another is called a gauge transformation. So let's derive now from scratch what these gauge transformations are for the electromagnetic potentials, simply from the condition that the electric and magnetic fields cannot depend on the gauge choice. In particular, we'll suppose that the vector potential can be transformed by adding to it a vector field alpha. Also, we'll assume that the scalar potential can be transformed by adding to it some scalar field beta. And it's important to note here that alpha is a true vector field that exists everywhere in space and can change in time. Likewise, beta here is a scalar field. It's something that exists everywhere in space and can change in time. So these transformations that I've written down here for A primed and for phi primed are of course the most general possible things that I can write down. So what is the condition that the physical properties remain unchanged? Well, I'll focus on the electric and magnetic fields. What we require is that the electric and magnetic fields obtained from the transformed potentials are equal to electric and magnetic fields obtained from the bare potentials. So, for example, we have that the magnetic field is given as the curl of the vector potential, and we can write the same thing down for a magnetic field obtained from vector potential A primed, and I'll call that magnetic field B primed. What we require is that B is equal to B primed. The physical observable, which is the magnetic field, is not changed. And what we want to know is what is the most general condition on A and A primed. Obviously, B is trivially equal to B primed if A is equal to A primed, but that's not the only thing that we can have. And what about for the electric field? We can say that the electric field is related to the potentials, first to the gradient of the scalar potential, and also through the time dependence of the vector potential. And similarly, we can say that the electric field in the primed system, E primed, is going to be the gradient of the primed scalar potential minus the time derivative of the primed vector potential. And again, the condition that we seek is that the electric field is unchanged by replacing A by A primed. So the electric field E must be equal to E primed. So this is what we require. Let's explore mathematically the consequences of these equations. And the way we do this, of course, is simply by substituting in our expressions for the gauge transformation, namely, as on the previous slide, that A primed is equal to A plus some vector field alpha, whilst our scalar potential phi primes is equal to our original scalar potential phi plus some scalar field beta. Remember, alpha and beta here are fields. And so we just want to substitute in these expressions for alpha primed and phi primed into our expressions for the magnetic field B primed and the electric field E primed. So how does that look? Well, B primed is equal to the curl of A primed, which is therefore equal to the curl of A plus the curl of alpha. The curl of A is, by definition, of course, the original magnetic field B. And the whole point is we want the magnetic field to be invariant to this transformation. And so on the right-hand side, this must be equal to B. The inevitable conclusion, of course, therefore, is that the curl of the vector field alpha must be equal to 0. And we've seen equations like this before. It's a constraint equation on the kind of field that alpha is allowed to be. In particular, we can actually introduce an auxiliary potential for the alpha field. Let's suppose that alpha is defined as being the gradient of a scalar field lambda. That has the nice property that if I take the curl of alpha, that is equal to the curl of the gradient of lambda, which, as an identity in vector calculus, the curl of the gradient is equal to 0, and of course this is what we want from this equation. So what we've achieved is we know that we can very generally add a vector field to our vector potential, and what we've learnt from this analysis is that the vector field we add to the scalar potential must be related to the gradient, or must be equal to the gradient of a scalar field if the magnetic field is to be left unchanged by the transformation. Okay, so let's move on to the second equation for the electric field. I'll write that E primed is equal to minus the gradient of phi primed, but we're writing that phi primed is phi plus beta, and therefore here I can write the electric field E primed is equal to minus the gradient of phi minus the gradient of the scalar field beta minus dA by dt minus d alpha by dt, where here I've substituted in for A primed the equation A plus alpha. And following the same logic, the idea is all of this stuff has to be equal to the original electric field. And of course, we know from the definition that this term and this term combined is giving us exactly the definition of the electric field. And therefore we have another constraint equation on the form of alpha and beta, namely that the gradient of beta minus the time derivative of alpha must be equal to 0. However, we've just worked out that alpha can be related to the gradient of a scalar field lambda, and so substituting that in, we can write this whole expression as the gradient of beta plus d lambda by dt is equal to 0. So what does this equation mean? The gradient of beta plus d lambda by dt is equal to 0. Well, the gradient, of course, means the spatial derivatives. So if this quantity beta plus d lambda by dt has zero gradient, it means that it does not depend on spatial position. So that means that beta plus d lambda by dt is a scalar field which we can call k, which only depends on time, doesn't depend on position. And of course, this k of t is something that's completely arbitrary. Beta was arbitrary and lambda was arbitrary, so of course k of t is arbitrary. So let's introduce yet another scalar field, psi, such that d psi by dt is precisely equal to d lambda by dt minus this arbitrary k of t. And using this definition, of course, we get that beta plus d psi by dt is equal to 0. And this definition here that we've used is basically equivalent to saying let psi equals lambda minus the integral of whatever function this was, k of t primed, let's say, dt primed. But given that lambda is completely arbitrary and k is completely arbitrary, then psi is completely arbitrary, and so we don't really need to trace through all of these definitions. It suffices to say that some function psi exists, which cancels off this k of t. So this is just a way of absorbing, if you like, into our definition of psi, the k of t function. And one other thing to note is that if we take the gradient of psi from the definition there, this is equal to the gradient of lambda, and we don't need to include any extra piece because, of course, the whole point is that the gradient contains spatial derivatives and our function k of t only depends on time. So the gradient of psi is actually equal to the gradient of lambda. Okay, so we can now put this back into our original expressions for the potentials. Previously, we had that alpha was equal to the gradient of lambda. We now have just shown that this is equal to the gradient of psi. And we have that beta is equal to minus d lambda by dt. And so plugging these expressions into our gauge transformations, we have our final result, which is that the vector potential A primed is related to the original vector potential A plus the gradient of psi, that's the alpha field, whereas the scalar potential phi primed, the transformed scalar potential, is equal to the original scalar potential phi plus beta, which is minus d psi by dt. And so these are the gauge transformations of the potentials that we've derived. And this gauge transformation of the potential depends just on this scalar field psi. And this scalar field psi is a function of spatial position and of time. And the important point about this, after all of this calculation, is that this scalar field psi can be absolutely anything. We can pick any scalar field psi that we want. There is one caveat, of course, which is this scalar field psi must be differentiable with respect to space and time, because that's the way in which it enters the potentials. And actually, it needs to be twice differentiable with respect to space and time, because to get the physical quantities, which are the electric and magnetic fields, we need to take the derivatives again of the scalar and vector potentials. But that's basically the only restriction. We can pick any twice differentiable scalar field psi. The way in which it enters into the potentials is very specific. The vector potential is modified by the gradient of this scalar field psi, and the scalar potential is modified by minus the time derivative of the same scalar function psi. So, just to emphasize, it's obviously important in these equations that we choose the same scalar function psi in both cases. And the important point, of course, is that the electric and magnetic fields are observable quantities, but they are invariant to the choice of psi. So E and B are so-called gauge invariant, meaning they do not depend on our choice of psi. And we know this because by construction we demanded that the electric and magnetic fields derived from these potentials do not depend on psi. So before continuing to actually use this gauge freedom to help us with our calculations, let's just take a minute to understand what we did here and what this result means. The gauge freedom that we see here, meaning the fact that we can modify our potentials by adding on this arbitrary scalar field psi, indicates that there's a certain redundancy within the description. There's a certain symmetry, if you like, that relates all the different A's and A primes related through these gauge transformations. So just the way if we were to have a certain symmetry in real space, a global symmetry, for example, a rotation, we would say that certain physical properties of our system, in fact, all physical properties of our system, don't depend on the rotation of our coordinate system. We would say that there's a certain redundancy in our description coming from the fact that space is isotropic and homogeneous. We can also translate our origin of our coordinate system, and that doesn't change the physical properties. So these are kind of global symmetries, and likewise we see that there's some kind of redundancy in the description when we're using potentials. We can do these kind of transformations and it leaves the physical properties unchanged. If I were to imagine making a transformation, a gauge transformation using a particular psi that did not depend on position or time, this would be like a rigid rotation that applied everywhere in space, and actually that would be equivalent to a coordinate transformation, and that would be a global symmetry of the system. However, here we have a much greater freedom. We can actually have this field psi change from point to point in space and also change in time, and yet the physical properties are left unchanged. So this is a much, much greater kind of symmetry than simply a global coordinate transformation. It's actually what's called a local symmetry. It refers to an internal symmetry of the potentials, and this is something that can be applied at every point in space and time. The set of possible gauge transformations forms a so-called group, and this is called the gauge group of the theory. In the case of a rigid rotation of our coordinate system, the gauge transformation can be thought of as simply a constant field psi, constant in space and time, and this gauge transformation affects the expressions that represent the rate of change along some path of some gauge-dependent quantity in the same way as those that represent a truly local quantity. However, a gauge transformation whose parameter is not constant as a function of space and time is a local symmetry rather than a global symmetry, and its effect on expressions that involve the derivative is qualitatively different from expressions that don't involve the derivative. And that's because the transformation itself is something that changes as a function of space and time. So when we do the derivatives, we pick up extra terms. And this is kind of analogous to a non-inertial change of reference frame, which produces, for example, a Coriolis effect in standard classical mechanics. Of course, here there are no pseudo-forces or anything like that, because the forces are observable, and these gauge transformations are certainly not observable. So electromagnetism is a theory, when cast in terms of potentials, that has these local symmetries. For these local symmetries, one can apply a local symmetry transformation, which is the gauge transformation, which means that the representation of the symmetry group is a function of the spatial position and time, and can be taken to act differently at different points in space-time. So our potentials have these internal symmetries, in addition to the usual global space-time-like symmetries. So we see here that there are symmetries of the problem that do not involve global space-time, like symmetries or transformations, and the components of the potentials transform into each other under this set of symmetries, and this is what we mean by internal symmetries. This concept of a gauge transformation characterizing a certain gauge theory is ubiquitous across many areas of physics. In particular, it's extremely important in general relativity and in quantum field theory. But here we see in the original classical field theory of Maxwell's electromagnetism, we see already this concept of gauge transformations, gauge symmetry coming out. And of course, it's rather interesting that the fundamental objects of our theory, which are these potentials, have within them this internal symmetry, whilst the observable quantities, which are the fields, the electric and magnetic fields and the forces and so on, the energy and so on, are actually blind to these internal symmetries. The final thing that I want to emphasize about this whole idea of gauge transformations is that to do any actual calculation, we must pick a specific gauge. So we must settle upon a particular convention in order to do any actual calculation. This is completely equivalent to saying in regular classical mechanics, we have a rotational symmetry or a translational symmetry. I can pick my coordinate axes any way I like, but when you actually come down to do a calculation, you need to settle upon a particular convention. You need to say, okay, here's the origin, I'm going to put it here. The x-axis is going to be orientated along this direction, and so on. And then when you've settled upon that definition, you can go ahead and do the calculation, knowing with confidence that had you chosen any other choice of origin and orientation of your axes, you would have got the same physical answer to observable quantities. This is a very important point. It means that whilst we have this gauge freedom, when we do actual calculations, we have to pick a particular gauge, and this concept is called gauge fixing. We need to fix a particular gauge to do a calculation. But it's not so bad. In fact, it helps us because we can judiciously choose our gauge to simplify to the greatest extent the equations. And I want to discuss a couple of different gauge choices now. One of the most famous gauges is the so-called Coulomb gauge. Here, we choose our auxiliary scalar field psi to cancel out any divergence that we have in the vector potential A. And what that means is that with judicious choice of our psi, we can arrange that the divergence of A is equal to 0, and of course that was what we had in magnetostatics. So the gauge freedom allows us to pick a specific gauge. We're doing gauge fixing, which results in a divergenceless vector potential. So what are the implications of this? Well, previously we plugged in the definition of the potentials back into Maxwell's equations to find a modified Poisson equation. We derived this expression, which is exact, by plugging in the potential, the electrodynamical potential, into Gauss's law. And of course, in Coulomb gauge, this term is equal to 0. And so we end up with the original Poisson equation which of course is a big simplification. So we can go ahead and use the Poisson equation here to calculate the scalar potential. And we already saw in the previous lectures how to solve the Poisson equation, the properties of the Poisson equation, and how to deal with these kind of systems of equations generically. But unfortunately, there's a bit of a catch, which is that we can't actually derive anything directly knowing only the scalar potential. We need both the scalar potential and the vector potential to work out the electric field, and the magnetic field is related to the vector potential. So solving this equation is not enough on its own to find physical observables. We also need to think about the vector potential. And when we plug the definition of the potentials into the Maxwell-Ampere law and use the properties of the Coulomb gauge, that the vector potential has no divergence, we still have an equation that is very messy. And indeed, we can see that it's coupled to the solutions of the equation for the scalar potential, because in here we see directly the time derivative and the spatial derivatives of the scalar potential entering. So there's no free lunch here, because in the Coulomb gauge, whilst we get a simple Poisson equation for the scalar potential, the vector potential expression is still rather complicated. From the Poisson-like equation for the scalar potential, we can obtain this expression, which is rather like the usual Coulomb law, hence the name Coulomb gauge. And the vector potential can, of course, be written in terms of the magnetic field, which takes this form. So here I'm not writing the vector potential in terms of the source field, which would be the current density, but rather the magnetic field itself. And these results are results that hold in Coulomb gauge. So if I only know the charge density and the current density, then I have to do a bit more work to actually use this formula in order to calculate the vector potential from the current distribution. But if I know the charge distribution and the magnetic fields, then I have enough to work out the potentials simply from these equations, and then I can plug that back in to work out the electric fields. And of course this works in a dynamical system. So this is one of the uses of the Coulomb gauge. If we treat the magnetic fields as kind of being independent, and we just think about the dynamics of the charge distribution in a background magnetic field, which we assume we know, then things become rather simple. So this motivates a certain set of approximations when doing calculations within the Coulomb gauge of electrodynamical systems. In particular, this is quite useful in semi-classical calculations for quantum mechanical systems, which involve electromagnetic interactions. One other comment on the Coulomb gauge is probably warranted, which is that these potentials that I've written down here, in terms of the charge distribution and the magnetic field, are apparently acausal. So what I mean here is these potentials appear to violate causality. This is not actually the case, but they appear to violate causality. So what do I mean by that? Well, imagine that I calculate the scalar potential according to this equation. And notice in particular that the time t on the left-hand side here is the same time t as on the right-hand side. What this tells you is that the scalar potential phi is determined by the charge distribution at a particular instant in time t. So if I move an electron in the lab, the potential on the moon, let's say, knows about this change instantaneously, even though the electromagnetic waves travel at most the speed of light. So it appears that the motions of the electric charge or the magnetic field appear everywhere instantaneously in the changes to the potentials. However, this is justified by noting that the scalar and vector potentials themselves do not affect the motions of charges and currents and so on. It's the electric fields that do that. The potentials are not actually observable. It's only the electric and magnetic fields that are observable, and actually it can be shown by direct calculation that there is no violation in causality on the level of the electric and magnetic fields. It requires a certain amount of time for the electric and magnetic fields to become updated when there's a change in the current distribution or charge distribution at a distant point. So there's no violation in causality here, but that's not manifest in the structure of these equations. And so a better way is to use a different gauge from the Coulomb gauge that I've written down here that actually makes these equations manifestly causal, and this will actually come in useful when we generalize this theory within special relativity in the next lecture. So let's have a look, therefore, at the so-called Lorentz gauge. In the Lorentz gauge, we make a very specific choice of our gauge transformation. We do a gauge fixing procedure, which results in a divergence of the vector potential, not equal to 0, as in the case of the Coulomb gauge, but equal to minus epsilon naught mu naught d phi by dt. So we're actually relating the vector potential, or the spatial derivatives of the vector potential, to the time derivatives of the scalar potential. And we can choose to have this in our gauge transformation because our auxiliary scalar field psi, which controls the gauge transformation, is something that can depend on both space and time. And so we can arrange by judicious choice of psi that the divergence of A is related to the time dependence of phi. And it can be shown that this is always possible to achieve. What is the consequences of this choice for Maxwell's equations? Well, when we plug in the definition of the potentials into Maxwell's equations, and we use the Lorentz gauge, we find a very pleasing symmetry between the equations controlling the vector potential and the scalar potential in terms of the currents and the charges, and they look like this. So first of all, we can write the vector potential in this form, which is actually decoupled on this level from the scalar potential. And we can write another equation for the scalar potential, which has exactly the same structure. And this is, of course, the nice feature of the Lorentz gauge, or one of the nice features. So in the first equation here, we have an inhomogeneous wave equation for the vector potential A in terms of the current density J, and in the second equation we have again an inhomogeneous wave equation for the scalar potential phi in terms of the charge distribution rho. The first equation is a vector equation, so there's actually 3 equations hiding behind here, whereas the second equation is a scalar equation. And so in the end, we have 4 inhomogeneous wave equations for the potentials in terms of the source fields J and rho. So this is a nice simplification. We've reduced the original 8 scalar equations contained within Maxwell's equations here to 4 scalar equations. And furthermore, here we have a nice symmetry between these 2 equations, and they're both simply inhomogeneous wave equations, which we have the mathematical machinery to solve. The symmetry in the structure of these 2 equations is no accident, and we'll return to that again when we look at the theory of special relativity within electrodynamics. Often these equations are presented in a slightly simplified fashion by introducing the so-called D'Alembert, which is this box squared symbol, not very visually appealing, but it's equal to the Laplacian minus mu naught epsilon naught d squared by dt squared. So this is an operator, And it just helps to simplify these equations a little bit. Notice also that this combination that we see here of mu naught epsilon naught featuring in all of these equations is actually equal to 1 over c squared. So when we're talking about these inhomogeneous wave equations, they contain in them some intrinsic velocity, and that velocity is the speed of light. So with that in mind, we can write down our equation for the potentials as D'Alembert squared, box squared, A is equal to minus mu naught J, and box squared phi is equal to minus 1 upon epsilon naught of rho. Just as a little heads up for what's coming later, we can actually then write this in a single four-vector equation in terms of the four potential A and the four current J. This is a four-vector equation, but precisely because this D'Alembertian is a Lorentz scalar, but we'll talk about that more in the next lecture. So let's actually go back and take the static limit. Let's solve these inhomogeneous wave equations for the potentials in the case where our rho is a scalar field that only depends on position rather than time, and our current density J is likewise a vector field that depends only on the position and not on time. This will then, of course, mean that the potentials do not depend on time. We can solve the wave equations then to get our familiar results. We get these familiar expressions, where this script r downstairs, of course, is the magnitude of the vector separation between the field point evaluated at a point r and the source point evaluated at a point r primed, which is then being integrated over. So what about the general solutions in the dynamic case, when the charge distributions and current distributions depend on time, and the potentials also depend on time? How do these equations get modified? Well, we know that now we have to solve inhomogeneous wave equations. What are the general solutions? In particular, because of causality, we know that in the dynamic case, it is not the charge density and current density at this current instant in time that matters, because at some distant point r primed, separated from the observer located at position r, the electromagnetic waves can travel only at a maximum speed, the speed of light. That's a finite speed. Therefore, the news, if you like, the information about the electromagnetic fields does not arrive instantaneously, but is delayed by a certain amount of time. Furthermore, that amount of time depends on the relative distance between the observer and the source point, and the total potential by the superposition principle is the sum of contributions from all different sources located at all different positions, and therefore we need to know information about the source fields ρ and j at all different times. How does this work in terms of potentials? This information can be contained in the so-called retarded potentials. So if I solve the inhomogeneous wave equations, I can show that they can be cast in the following form. First, for the scalar potential phi in the dynamical case, so let me just emphasize that this is really the dynamical case, where everything is time dependent, I can write the solution to the scalar potential in terms of the charge density at some particular source point r primed, and at some particular time I'll call tr divided by the script r, which is the separation between the source point and the field point as before. However, so this looks exactly like the case of the static potential, except I've replaced on the right-hand side of the equation the time t, which appears on the left-hand side of the equation, by something different. I've replaced it by tr. tr is the so-called retarded time. I'll say more about that in a moment. Let me first write down the form of the vector potential at a position in space r and a time t. I can write that in terms of the current density evaluated at some source point r primed, and again at some retarded time tr. And then I integrate over the source points. Again, the script r is the separation between the field point r and the source point r primed. So these equations look exactly the same as in the static limit, except we use the retarded time. And the retarded time, t subscript r, is the actual time appearing on the left-hand side of the equation t, minus the separation divided by the speed of light. So this script r here is exactly this distance between the source point and the field point. And this is a very important equation, the definition of our retarded time. What is the retarded time? So you can see that the retarded time is a space-dependent time that is earlier than the present time. The current and the charge distributions at a given instant in time t cannot affect the potentials at a distant location because the information, which is an electromagnetic signal or electromagnetic wave or whatever, needs to travel through space at a distance of this script r, and it can only do that at a finite speed, c. And it has to travel through space at that speed to reach the point of interest, the field point. So the current and the charge configuration at an earlier time, which is this retarded time, affect the potentials separated by a distance of script r at a time t. So we need the entire history of the source fields ρ and j in order to calculate the retarded potentials. So these equations actually hide within them some complexity. They look exactly like the static potentials, but because we're evaluating these things at retarded time, things are much more complicated. In particular, you see that as we're integrating over different points in space, we actually need to know the potentials at different times through this equation. So if we know the entire history of the source fields ρ and j, we can calculate the potentials, and then from those we can calculate the electric and magnetic fields in the usual way. These retarded potentials are therefore a very, very convenient and nice, powerful way of keeping track of not only the charge and the current distributions, but the history of those things and how they've changed, because the way in which they change affects the electric fields and the magnetic fields, not only now, but at different points in time as well. So I haven't actually proved that these retarded potentials are the solutions to the inhomogeneous wave equations, but I've written them down here, and what you can do is just plug them into the inhomogeneous wave equations and show that they're satisfied and that these equations are actually the proper solutions. I won't do that, I'll leave that for you to try. It's a little bit of a complicated calculation because you've got to remember that the time entering in here, the retarded time, is actually space-dependent. Note, however, that there is no such thing as retarded electric and magnetic fields. We have a concept of retarded potentials coming through this formulation that I've described, but there's no such thing as a retarded field. We can't think of the fields directly in terms of the charge density and current density at the retarded time. So the dynamical world is not as simple as simply replacing time by retarded time. That's actually something that's specific to the potential formulation, and indeed that's one of the main reasons why we want to use this potential formulation. So if the electric and magnetic fields are not just obtained by replacing time by retarded time, then what are the electric and magnetic fields in the dynamical case? Well, since we have the potentials now, we can simply calculate the electric and magnetic field through the usual equations. So from these retarded potentials, we just obtain the electric and magnetic fields as usual. These fields involve space and time derivatives of the potentials, and remember that the retarded time featuring in these potentials is something that depends on both space and time, so we pick up some extra unexpected terms. And when we do that, we obtain Jefimenko's equations, which can be viewed as the causal solutions of Maxwell's equations. So let's see what we get. For the electric field, we obtain this expression, which is basically the time-dependent version of the Coulomb law. We see the usual static contribution to the Coulomb law, but then two additional time-dependent pieces, one coming from the time dependence d by dt of rho, which I've denoted here as rho dot, and d by dt of j, which I've denoted as j vector dot. Notice also, of course, that in the dynamical case, all of these fields are evaluated at the retarded time t sub r. What about the magnetic field? This is the result, which is thereby a time-dependent version of the Biot-Savart law. And again, we see that the first term is basically the usual expected piece for the static limit, albeit now evaluated at the retarded time, t sub r, and then we have a new contribution to the time dependence of the currents, which are given by this d by dt of j vector, which I've denoted here as j vector dot. And again, everything is evaluated at retarded time. So these are the causal solutions to Maxwell's equations. These are the full solutions that if I know what's going on with the charge density and the current density as a function of time and space, then I can use these equations to find the electric and magnetic fields. So at the start of this lecture course, we said that one of the main aims in electrodynamics, one of the main goals, is really to figure out what the electric and magnetic fields are doing due to some particular charge and current configuration, and here it is. These are the final solutions to that problem. Actually solving these things is a different matter, but at least now we know what the equations are. So let's now consider the electrodynamics of a single point charge that is moving. So let's draw a little diagram. First of all, we'll draw on the point charge itself. This is something that has charge q, and we'll say that it's moving along with some particular velocity v. Let's say that the trajectory of this particle is something that changes with time. Let's call that w of t. And that vector w is defined with respect to some origin of our coordinate system. Just arbitrarily, let me define it up there. And this w is precisely this vector. That goes from the origin to our point particle. And note, of course, that w is something that's time-dependent because the particle is moving around with our velocity v. In principle, the velocity v could also be time-dependent v of t. So what we want to know is the value of the potentials or the value of the fields at some other point. Let's say this red point over here, which is the observer. So this is the so-called field point, whereas the charge is the so-called source point. And this observer is located at a point r in space, which is a vector, again, determined relative to our origin. And so I'll call that r vector there. So just for future use, let's imagine that we have an instantaneous vector at a given instant in time that connects the point charge to the observer. I'll call that vector capital R, and the angle it makes with the direction of travel of the particle, I'll call that theta. However, to work out the retarded potentials, we actually need to know the position of the particle at the retarded time. What this means physically is that at a given instant in time for the observer, the information about where the particle is actually relates to an earlier time, the retarded time, and that's because it takes a finite amount of time for the electromagnetic information to travel to the observer. It does so very quickly at the speed of light, but it's not instantaneous. So we have to consider the particle's position at an earlier time, and therefore it was located at a different point in space. So let's illustrate this with a cartoon. Consider a snapshot of the situation at a time tr. This is the retarded time. The particle is moving along, let's say the x-axis, and at that instant in time, the retarded time, the particle emits some electromagnetic waves, let's say, some information about where the particle is. And I'll sort of just denote this as these sort of, suggestively as these sort of spherical wavefronts emerging from the particle. At a later moment in time, the particle has moved over here. I'll draw this with an open circle to indicate that it's a later point in time. And it's still emitting the radiation. But the original radiation at this later time has now also moved out. And then as the particle moves another step in the next instant of time, the original radiation again continues to move out, and so on and so forth. So as I consider these snapshots in time moving forward, this radiation approaches the observer, and finally, when the particle is over here, the radiation reaches the observer. So at a time t, the particle is located over here, and it's only at this point at time t that the observer gets the news about the position of the particle, but the news that it gets is about this original position of the particle all the way over here. So I'd have to wait quite a bit longer for the observer to get news about the position of the particle at time t, and by then the particle will have moved even further to the right-hand side. So in this sort of cartoony illustration, you can see that because the light moves at a finite speed, which is the speed of light, it's actually not the instantaneous position of the particle that matters, it's this retarded position, and the retarded position is basically the position of the particle at the retarded time. So if w of t is the instantaneous position of the particle at time t, then we can write the retarded position as being defined by the separation between the observer and the particle, but evaluated at the retarded time. And the retarded time is itself implicitly defined by this equation. So this is the usual expression for the retarded time, but now written in terms of this retarded position vector. So we can plug these expressions into our retarded potentials for the case of a single moving point charge and obtain the retarded potentials. And after quite a bit of lengthy algebra, which I'll spare you, one obtains these retarded potentials. So let's just unpack what's written here. First of all, this is the scalar potential evaluated at an observer position or a field point r at a given instant in time t. It is related to this retarded position, which is this script r here, which is defined in this way that we were just discussing. And this v vector here is the velocity of the particle. We also find that the vector potential A, again evaluated at the same field point of the observer r and at the same time t, is related to the scalar potential. Actually, the prefactor is just the velocity of the moving charge v divided by c squared. So these are very famous forms of the retarded potentials called the Lienard-Wiechert potentials. And these Lienard-Wiechert potentials tell us about the potential for a single moving point charge. Now, instead of writing the expressions for these retarded potentials here in terms of the retarded position, which we needed in order to be able to do the calculation, let's now write it at an instantaneous moment in time in terms of the vector at this particular instant in time connecting the particle to the observer, and the angle between that vector and the velocity of the particle, the direction of travel of the particle. So this is the situation. We imagine the particle is just moving along, for example, along the x-axis with a velocity v, and instantaneously it makes a vector capital R with the observer with an angle of theta, and just plugging it into the equations a little bit and manipulating, it's not hard to see that the potential at the observer located at position R and at an instantaneous moment in time t is equal to 1 over 4 pi epsilon naught capital R. Capital R here is the length of the vector R, times q over the square root of 1 minus v squared over c squared sine squared theta. That's just coming from the dot product in the previous result. And then, as before, the vector potential at position R and at time t for the observer is just equal, again, to this velocity v divided by c squared of phi of R and t. These are not retarded times. And the important point I want to emphasize here is that if we were to look at the non-relativistic limit, we haven't talked much about relativity yet, but the non-relativistic limit is obviously v much less than the speed of light c. So we're talking about the particle here, the point charge particle, moving with a velocity that's much less than the speed of light. Then we see that this quantity downstairs here, v squared over c squared, gets very small, and in the non-relativistic limit we get that the scalar potential basically goes to q over 4 pi epsilon naught r, which is the usual electrostatic result. This is the usual Coulomb law for the electrostatic potential. So if the particle is moving slowly, then we see basically the static limit, the non-relativistic limit is the static limit, but at any finite velocity, we do pick up corrections of this form, and this is a very characteristic form of things that change in special relativity. And in particular, as the velocity gets large compared with the speed of light, this becomes a very significant warping and distortion to the form of the scalar potential. Notice also that we actually get some magnetism coming out from the moving point charge, but that becomes very, very small because we have this quantity v over c squared here in the non-relativistic limit. Again, if the particle is moving quickly, then we'll see a magnetic field generated from this vector potential. In the non-relativistic limit, though, when v is much less than c, that's the magnetism generated by the moving point charge becomes very small. So what else can we do with these potentials? Well, obviously, we'd like to know the electric and magnetic fields from these potentials, not in the non-relativistic limit, but in the general case. And we can do that by simply using the usual expressions for the electric and magnetic fields expressed in terms of these potentials, Or we could simply use directly Jefimenko's equations, where the charge density is the specific charge here moving along with a trajectory specified by W of t. And I will spare you the derivation of that, but here are the results. So this is what we get for the exact form of the electric and magnetic fields due to a single point charge moving along with a constant velocity. So here I am assuming that dv by dt is equal to 0. The particle is not accelerating. We get slightly more complicated expressions if the particle is also accelerating. Here I'm just considering a uniform motion. And the way I've drawn the diagram here, we have an instantaneous unit vector between the particle and the observer, characterized by capital R and angle theta to the direction of travel. And it's this vector r that is featuring in these equations. And v is the velocity, and we see these velocity-dependent factors coming into the equations for the electric and magnetic fields. And we can see a couple of very important things here. One is that the electric field, the direction of the electric field is radial. So we see here that the electric field is always pointing in the r hat direction. We also see that it has a 1 over r squared behaviour, just as the usual Coulomb law. However, that magnitude is also velocity dependent for a moving point charge, and so we will see a angle and velocity dependent modulation of the field strength. The direction of the field lines is still radial, but the field strength is now velocity and angle dependent, the angle coming in down here. We can also see that we have this v squared over c squared factor coming in, and that means that in the non-relativistic limit, these factors go to 0, or tend to 0, and then we're just left with this original factor here, which is the usual Coulomb law. So the non-relativistic limit gives us back the static limit of the Coulomb law. However, for finite velocities, we get corrections. We'll see later that these are relativistic corrections. What about the magnetic field? Again, the magnetic field is very much smaller than the electric field. We're down by a factor of v upon c squared. So in the non-relativistic limit, again, this vanishes. We also see that the magnetic field is perpendicular to the electric field everywhere, and that it's curling around the direction of velocity. So we can regard a point charge that's moving along with constant velocity as like some kind of current, essentially, with the magnetic field resulting from that being something that curls around the wire, so to speak, which is just the direction of travel of our point particle. So how does this actually look? Let's plot these electric and magnetic fields. So what I've plotted here on the diagram is a very badly drawn sketch of the electric field, and what I'm seeking to show with this sketch is that the field lines are still radial, pointing out instantaneously away from the moving point charge. However, the electric field strength becomes very much focused in this perpendicular direction, and it's much, much weaker. There are fewer of these field lines in the direction of travel. And notice that this anisotropy of the field strength is something that's controlled in v squared over c squared, so only becomes very noticeable when the particle is moving very quickly. In the non-relativistic limit, we don't notice this effect, and everything looks isotropic. So let's have a look now at the magnetic field. So this is what we see for the magnetic field. It's something that is curling around the axis of the travel of the particle. So it has some properties of the magnetic field that one would expect from a current moving down a one-dimensional wire. And it has this sort of curling property that, notice, satisfies correctly the right-hand rule, as we might expect for a current down a wire. But it has this interesting dependence of the field strength depending on the position, with the field strength attenuating as we move away forwards and backwards from the particle in the direction of the travel. The largest amplitude for the magnetic field, as with the largest amplitude for the electric field, is in this perpendicular plane at the current location of the particle. So if you can imagine in a wire, this wire being made up of lots of these point particles moving along with a constant velocity, one could imagine using the superposition principle to superpose lots of these magnetic field lines like this and producing in general something that is translationally invariant down the length of the wire and simply has this curling structure of the field around the wire. So I want to end this lecture with doing a couple of examples of using this formalism, of using these retarded potentials and so on to calculate the electric and magnetic fields for some particular dynamical situations. The first example I want to consider is the electric field due to a steady current. So previously, of course, we've looked at the magnetic field due to a steady current. Now let's have a look at what the electric field due to the steady current is using these retarded potentials. So the first step is to notice that our current density, J of R and T, is time independent if it's a steady current. So this is constant in time. Another way of saying that is that J vector dot is equal to 0. This is, of course, the situation we considered in magnetostatics, and yet, in some sense, this is still a dynamical situation. We do have charged particles in motion, so this is still a dynamical situation. These charged particles constitute a steady current, but we've never really considered this steady current to be a dynamical situation before. But in fact, the particles are moving, and so what does this imply for the electric field? So first of all, let's start from the continuity equation for the conservation of charge, which always holds. And we know that the divergence of the current is minus d rho by dt, where rho is the charge density, and I'll just write that right-hand side here as minus rho dot, the time derivative, and integrating that with respect to time, we find that rho, of course, is minus the divergence of J times the time t plus a constant. And we can do this because we know that the divergence of J is independent of time, and that's because the current itself is independent of the time. So if the divergence of J is independent of time, we can look at time t equals 0. And in that case, rho is just equal to the constant. So obviously the constant is equal to the charge density evaluated at t equals 0. If we were to then take the time derivative of both sides of the equation, we'd learn that minus the divergence of the current was equal to rho dot. And therefore we can write, where here I'm writing the time derivative of the density rho dot at time t equals 0, because that's not something that depends on time. So I can pick any time, and I choose t equals 0. And in the end, of course, this is nothing more than a Taylor series expansion of rho around t equals 0, and we see that this is the exact solution with no higher powers of t, precisely because the current is time independent. So let's now work out the electric field from Jefimenko's equations. And we can drop the piece with J dot because that's equal to 0. And this is what we get. Notice, of course, that in this expression for the electric field, we have the retarded time featuring, and the retarded time is, of course, given here, is defined here, in terms of the separation between the point being integrated over r primed and the field point r. That's what this script r thing is that features in this expression. So let's now just substitute in our expression for rho of r and t, and we can also take the derivative of rho and r and t and plug that into this expression and see what we get. This is the expression, and now we can actually substitute in this definition of the retarded time actually in here. And that gives us a fortuitous cancellation, because we have one term with rho dot over script r squared times t, but the other contribution is minus rho dot of 1 over script r c, and that cancels with this second term here. So we get the following. And the nice thing about this expression is that comparing it to this equation here, we can actually see that this object inside the square brackets here is actually nothing other than the charge density at position r and its time t, not retarded time tr, but at real position t, divided by script r squared. And of course, magically, this is Coulomb law from electrostatics. And so what we see from this is that contained within these general expressions for the electrodynamical case, if we consider the limit of a steady current, then we can actually derive Coulomb's law from this. Even though a current constitutes moving charges which are dynamical in nature, we see that that's not a problem, because if we have a steady current, then we get back the electrostatic situation, and Coulomb's law then holds. So when the current density J is constant, rho is of course not constant in time, so it's not really electrostatics, it's a proper dynamical problem, but it's just fortuitous that Coulomb law holds in this special case, and we see that emerging from the analysis here. So very nicely, we see that electrostatics holds in the case when we have time-independent currents. The electric and magnetic sides of the theory indeed do decouple in the static limit. And notice from this Coulomb's law something very important. The charge density that features in here is evaluated at the current time t, not the retarded time. So let's have a look at another example. This is going to be on the validity of the quasi-static approximation. In the previous lectures, when we were talking about dynamics in the context of inductance and so on, and the flux rule, we came across this idea of the quasi-static approximation. And that was where we used the Biot-Savart law, which is of course a law coming from magnetostatics, in the situation where we have time-dependent flux or time-dependent magnetic fields. And of course that's not allowed, because the Biot-Savart law is something that applies strictly in the time-independent case. However, I mentioned back then that actually the quasi-static approximation, where we just go ahead and use the Biot-Savart law anyway, actually turns out to be rather a good approximation. And now we're actually in a position to test that statement and to understand why it is that the quasi-static approximation is actually better than you'd expect. The first step is to write down our current density, J of TR. We're going to consider the current at a retarded time TR, and we're going to do a Taylor series expansion of this current density around the time t. Not the retarded time, but around the time t. And therefore, we get a Taylor series expansion that looks something like this, in powers of TR minus T. And higher order terms, which I won't actually write. Notice already here that this quantity TR minus T is minus the separation divided by the speed of light. And so a power law expansion of the current density in powers of TR minus T, this Taylor series expansion, is something that's justified if we have a slowly varying or slowly changing current. So we're considering here a slowly varying J of TR. Good. So let's use that. Let's use this expression where we've expanded the current density at the retarded time around the present time. Let's just use these first two terms, the zeroth order approximation and the first order term. We'll just substitute that into Jefimenko's equations for the magnetic field, and we'll see what we get. So here is Jefimenko's equation for the magnetic field in the case that we're interested in, and here I want to now substitute in the J of TR in terms of J of T and J dot of T. And so we have this expression. And here I just used the fact that this combination here is minus script R over C. That's where this factor comes in. And this factor, the second term in the original expression, is still here. It's the same thing. Notice in particular, these first two terms are evaluated at time t, whereas the third term here is evaluated at the retarded time tr. So how can we use our expression, our Taylor series expression for J of TR to extract the time derivative J dot of TR? So let's just take our expression for J of TR and take the time derivative. So what we're interested in, what we want to know in our expression is J vector dot of TR. And what we mean by that dot in this case is d by dtr. It's the derivative with respect to the retarded time of J t retarded. On the right-hand side of the equation, the first term doesn't depend on the retarded time. It's completely constant, so that's equal to 0. In the second term, we have a J vector dot of t. Again, that's constant in terms of retarded time, but we do have this factor of the retarded time sitting out the front here. So when I take the time derivative with respect to this term, I'm actually just going to pick up a factor of J vector dot at time t, and there will be higher order terms, but they're of order J double dot of t, and I'm going to neglect those because we're talking about a slowly varying current. So what we learn is that J vector dot at the retarded time to first order is equal to J vector dot at the current time t. I can substitute that result in here. And what do I get? I get the following. And something very interesting happens, which is that these two terms, one from here and one from here, actually cancel out. Notice that this happens to order J double dot. So if we have a slowly varying current, then we can neglect those higher order terms, and then these two terms in here cancel, and then that's it. If we had a more quickly varying current, we'd have to include higher order terms in our Taylor series expansion of the current, and then there would be higher terms featuring in this expression here. But to this order of approximation, these two terms fortuitously cancel, and what we're left with is the standard Biot-Savart law for the magnetostatic case, namely mu naught upon 4 pi of the integral of the current density evaluated at the present time t, not the retarded time, and then integrated. So this is, the punchline of this is that this is the Biot-Savart law for magnetostatics at the non-retarded time. So this is just the usual magnetostatics result. So this is actually extremely interesting because what it tells you is that if my currents are varying rather slowly, then I can do to first order this Taylor series approximation, and fortuitously these terms cancel out, and what I'm left with is that the magnetic field is actually given by the Biot-Savart law. So even in the dynamical case, when I have time-varying currents, as long as the currents are not varying too quickly, you can actually use the Biot-Savart law. So there's a kind of cancellation of errors, if you like. We have two errors in this expression, if you like. One of them is that we're neglecting the changing current density to higher orders. And the second thing we did is we're evaluating the current not at the retarded time, but at the present time. They're the two things that are different in the Biot-Savart law than from the full dynamical situation. And if the currents are varying slowly, what we've proved here is that those two errors cancel out. We can neglect the higher order terms in the expansion of J, and we can also just use the current time rather than the retarded time. And making those two changes together restores the Biot-Savart law for magnetostatics, and the two errors cancel out. So this is the quasi-static approximation. It's basically to say, even though we have a dynamical situation, let's just go ahead and use the magnetostatic result for the Biot-Savart law anyway, and actually, this approximation is better than you'd think. It holds to first order in the time dependence rather than just to zeroth order. It's not exact, but it's a good approximation in cases where the current densities are not changing very quickly. Good, so we covered many things in this lecture. We talked about potentials. We talked about how when we have a full dynamical situation, we have to be more careful with the potentials. We looked at the concept of a gauge transformation, which has behind it this fundamental idea of hidden symmetries, local degrees of freedom, which are kind of transformed within the potentials. There's a local symmetry from point to point and in space and from time to time. And the gauge transformation is like a local symmetry transformation between the elements of the potential. We use that in the Lorentz gauge to show that we can write down inhomogeneous wave equations for the potentials, and that led to this idea of the retarded potentials. From that, we calculated the potentials and the fields for a single moving charge, and we saw that this generalizes the result for electrostatics and magnetostatics. And then finally, we did a couple of examples, in particular, putting on more firm footing this idea of the quasi-static approximation. Okay, so in the last lectures of this course, we'll look at the relativistic formulation of electrodynamics, which builds heavily upon these concepts of the potentials.